Now I'd like to look at an example of finding area in polar coordinates that involves the area between two curves. So let's find, say, the area that is inside r equal 2 cosine 2 theta and outside r equal 1. So let's draw a picture. We really can't write an integral just by looking at these equations because we don't know where this area is located, where it starts, where it stops. So let's sketch a picture. Let's do that r equals 2 cosine 2 theta. Now, you may recall when I introduced sine and cosine theta, that gave a circle, right? It gave a circle either up here on the y-axis or over here on the x-axis. For cosine, it was over here on the x-axis. But when I started compressing the wavelength there, or the period, you started to get leaves, right? And you got twice as many. When it was even, you got twice as many. So I know this has 4 leaves, but I don't really remember off the top of my head where they're oriented. And the easiest thing to do is, if you think about those leaves, every leaf starts and ends with you at the origin, right? So all I really have to do is figure out when is this equation at the origin. And what is the origin? The origin in polar, remember, is r equals 0. So if I just set this equation equal to 0, and actually the 2 has nothing to do with it, right? I can divide that out. So I'm really interested in when is cosine 0. Well, it's when the angle, so it's when the thing inside, and 2 theta in this case, is equal to, well, when is cosine 0? Cosine is 0 at plus or minus pi over 2, plus or minus 3 pi over 2, and so on. There's going to be some repetition, obviously, because it keeps going round and round and round. And then we divide by 2. We see that our angles are plus or minus pi over 4, plus or minus 3 pi over 4, and so on. So what I'm going to do is, the way to think of these angles is that's where we're at as we enter the origin. So we're getting, as we get closer and closer to that origin, that angle, we're diving in. So for example, I'm going to draw a little, like you know how when we would draw asymptotes, right? Long run behavior, we'd sometimes put that in as a guide. Well, as I come into the origin, I'll be coming in as I get close to pi over 4, or negative pi over 4, or negative 3 pi over 4, or positive 3 pi over 4. So I'm just putting those in as guides as I draw this. So now I know where my 4 leaves are, right? They're in between there because each leaf is going to start and end as it approaches those asymptotes. And how big do they need to be? Well, the biggest cosine ever gets is 1, and this is multiplied by 2. So at the very tips of those leaves, we're out here at 2, 2. Try and make it symmetric here. 2. So try and draw your leaf so its max here is 2, and then it's becoming asymptotic to that dashed line as you enter the origin. And you'll get a rough sketch of. And so all those leaves should look the same. I didn't quite get my axes labeled perfectly even. That leaf looks a little bigger. But they should be all the same size, right, because of the periodic nature of cosine. So we want to be inside those leaves. But outside r equal 1, and that's simply a circle, right? All the points 1 unit from. So let's draw our circle. Okay, now what I'm going to do is only do one of those. All the regions we're looking at, let's put in some shading there. So I want to be inside the leaf but outside the circle. So imagine radii coming out from the origin, but they're only extending from the pink there to the yellow. There's one of our regions, right? And there's actually 4 identical ones. And so I'm just going to figure out the area of this region and multiply by 4, since all 4 of them are going to be the same. Okay. So let's think about this. I want to start here and end here, right, at those points of intersection. So I'm going to need to set those two equal to each other to figure out what those points of intersection are before we can begin. So I want to know, when is 2 cosine 2 theta equal to 1? Well, that's when cosine 2 theta is equal to 1/2. And I'm really just interested in these first 2 times, right? That first negative and that first positive. So cosine is 1/2 at what? Pi over 3. So plus or minus pi over 3. So when I divide by 2, we're talking about plus or minus pi over 6. So all I'm going to do is an integral from negative pi over 6 to pi over 6 to get that one leaf, and then multiply by 4. So let's set that up. So first of all, it's going to be 4 times. Now I'm going to do this separately first, but we can always combine these together into one integral. Really, that area is the area inside the leaf. So we're going to take that integral, and then we're subtracting out what's inside the circle, right? Because it's really trapped between there. So from negative pi over 6 to pi over 6 of 1/2 that leaf function squared. But that would give me everything from the origin all the way out, right? So it would be shading in here as well. I don't want to be shading in there, so now I need to take out the area inside the circle. So that's from negative pi over 6 to pi over 6 of 1/2 that function squared. Now, this is very similar to what we did at the very beginning of the semester in Cartesian when you wanted the area between 2 curves vertically or horizontally. It was bigger minus smaller, bigger minus smaller. Well, bigger means in terms of r. Well, bigger in terms of r means farther away from the origin, right? So the leaf curve is farther from the origin. The circle curve is closer, so it's bigger minus smaller. The limits are the same, so you could combine that into a single integral, which is what I'm going to do. So I'm going to take the 1/2 out completely and multiply by the 4, first of all. And so then we would have the integral from negative pi over 6 to pi over 6. And again, you could take advantage of symmetry yet again, right? This leaf has a symmetry across the x-axis. So we could actually go from 0 to pi over 6 and double it again. But I won't bother with that this time. So that's 4 cosine squared 2 theta minus 1. Just squaring that. And the 1/2, remember, has already come out. D theta. Again, we're going to see lots of sine squareds and cosine squareds, so we want to use our identity. Cosine squared is 1/2 1 plus cosine of twice the angle. We got to be a little careful here. The angle's already 2 theta, so when we double it, it's going to get 4 theta. The half in the identity is going to make that 4 a 2. So it's going to be 2 plus 2 cosine 4 theta. So instead of 1/2 plus 1/2, multiply by 4, it's 2 plus 2. Cosine 4 theta minus 1. Two minus 1 is 1. So integral of 1 is just theta. Here we're going to have to divide by 4, so that's 1/2 sine 4 theta. From negative pi over 6 to pi over 6. So pi over 6 into there gives us pi over 6. Here, that's sine of 2 pi over 3, right? Which would be square root of 3 over 2 times the half. So square root of 3 over 4 minus a negative pi over 6. And sine of negative 3 pi over 2, that's just the negative of that. So negative square root of 3 over 4. These are the opposite of these, but it's subtraction, so it ends up reinforcing. Those all end up double what they were. So double what they were, but it was already double, so 4 times pi over 6 plus square root of 3 over 4. And we could bring the 4 through if we wanted, so that's 2 pi over 3 plus square root of 3. All right, so you had a few options. You could have done any of the leaves. You definitely only want to do one of them. You don't want to do 4 integrals because they're all the same. So I just picked this one because it's in the range where we're very familiar with our angles. So I just picked that one. There's 4 of them. The bigger minus the smaller because that shading is trapped between the 2 curves. We'll look at another example where it involves 2 curves, but it's not trapped in between. We'll look at that example next.